Hey guys, and welcome to the first lesson of Unit 4, 4.1 Review of Trig Identities. Now, an important thing to note is that a trig identity is any mathematical equation that's true for all values of the variable. Okay, so for example, we have 7x minus 3x is equal to 4x. This is true for all values of x. And that's the important thing with identities. Now, a trig identity obviously is an identity that has trig expressions. In grade 11 and in the last unit, we came across these particular identities. We have a quotient identity, which is tan theta being equal to sine theta over cos theta, and we talked about the Pythagorean identity where sine squared theta plus cos squared theta equals 1. And we also talked about how we could rearrange that Pythagorean identity so that sine squared was isolated to be equal to 1 minus cos squared theta, or when cos squared was isolated so that we had 1 minus sine squared theta. We also talked about the reciprocal identities, so that cosecant theta is really 1 over sine theta, secant theta is 1 over cos theta, and cotangent is really 1 over tan theta. Similarly, if tan theta is sine over cos, then cotangent would be the reciprocal of that, so cos over sine. When you are proving an identity, the things you can do is you can work with just the left side so that it ends up looking like the right side, or you can work on the right side so that it works on the left side, or you can work with both sides until both sides equal each other. Okay, so basically your end goal is you want left side to equal right side. In order to do this, we can do some substitutions based on the identities that I showed you on the previous slides. We can do some algebraic manipulation. The one thing that you cannot do is do not move terms from one side to the other. Okay, so everything that's on the left side will stay on the left side, and everything that's on the right side will stay on the right side. Do not start moving terms from one side to the other. Okay, so what we'll do is work on a few examples. So on our left side here, we have cosecant x minus sine x, and separately on our right side, we have cotangent x times cos x. Now, like I said, you can work with one side, you can work with the other side, or you can work with both sides. Ideally, the best thing to do is always change these into terms of sine and cos. So on our left side here, I can change this cosecant to 1 over sine x. Now, essentially what we have here is two fractions that are being subtracted, because this sine x is really sine x over 1. Now, in order to add or subtract fractions, we need a common denominator. Our common denominator would be sine x. So in order for me to get that common denominator, I'm going to take the second fraction here and multiply both top and bottom by sine x. And then what we're left with is 1 over sine x minus sine squared x over sine x. And really, I could have written this as one big fraction over sine x, and we're left with 1 minus sine squared. Now, if you'll remember from the first slide, 1 minus sine squared x is really part of the Pythagorean identity. That is equal to cos squared, and now over sine x. And really, we've worked our left side probably to be as simplest terms as possible, so cos squared x over sine x. There's not really much more that we can do on that side. So I'm going to go ahead and start working on the right side and hopefully make it look like the left side. So cotangent x, we said was the reciprocal of tan. We also know that it's equal to cos x over sine x. So cotangent times cosine. Now, again, we have two fractions being multiplied, and when you're multiplying fractions, it's numerators times numerators, giving us cos squared, and denominators times denominators. So sine sine times 1. Now if you'll take a look, we do end up with left side equaling right side. And so just to finish a proof, you end up saying QED, which really means it has been proven. Okay, so we'll move on to the next example. If you wanted to challenge yourself, you can always pause the video right here and try the work on your own, and then play the video and see if you get the same answers that we get. Alright, so again, separately work with your left side, and then our right side is separate 1 over secant x. The right side is very simple. 1 over secant x is really just cos x. So right side is now in simplest form. Now on the left side, I have two terms here. They're all in terms of sine and cos, so there's no real substitution that I can do. But I do know that in both of these terms, we have a cos x common to both. So I'm going to factor out that cos x, leaving me with sine squared x plus cos squared x. Now again, the sine squared x plus cos squared x is the Pythagorean identity, and that when you add these two together, it ends up being 1. So cos x times 1 is just cos x. So as you can see, left side equals right side, and it has been proven. Moving on to example C. So on our left side and on our right side, okay, so if we were to work on the left side, well, I know that 1 over tan squared x is equivalent to cotangent x. And if I wanted to change this into terms with sine and cos in it, well, cotangent x is really just cosine, but because this is tan squared, it'll be cosine squared x over sine squared x. And the other thing is we have a plus 1. What I'm going to do here is, because I have a fraction, I'm going to change this into a fraction with a common denominator. So our denominator would be sine squared. So I would multiply both top and bottom by sine squared x. And that will give us one big fraction. So our common denominator is sine squared x. And then we're left with cos squared x plus, and then 1 times sine squared. So sine squared x. And again, here comes that Pythagorean identity again. Cos squared plus sine squared does equal 1. So we're left with 1 over sine squared x. And that's pretty much all we can do with the left side. If we go back to our right side, cosecant squared x is really just 1 over sine squared x. And if you'll notice, we end up with the same value or the same expression on both sides. So left side does equal right side. It has been proven. And finally, our last example. This one I'm going to show you two different methods. So I'll separate our left side and right side. Now looking at the left side, I have 1 plus cos x. There's really not much I can do there. Everything's already in terms of sine and cos. And this 1, I'm just going to leave it as is. I'm going to take a look at the right side and we're going to work with that. Okay, so as I said, this will be method 1. Now, in method 1, what I'm going to do is, I see that I have a sine squared up in the numerator, so I'm going to use that Pythagorean identity to replace sine squared. We know that sine squared is equal to 1 minus cos squared x. Okay, now in the numerator, you'll notice that we do have a difference of squares. So we are going to square root each term. So square root of 1, square root of cos squared. One bracket gets a minus sign, and then one bracket gets a plus sign. And this is still all over 1 minus cos x. Now, because we have two binomials being multiplied, I can start to cross out. So I can cross out this entire binomial with this entire binomial on the bottom. And so that leaves us with just 1 plus cos x. And you can clearly see that left side does equal right side. Now, method 2. In method 2, we're going to use something called the conjugate. And you're probably familiar with the conjugate when you are rationalizing denominators. Now, so what the conjugate is when you're looking at this denominator, I see a 1 minus cos x. So what we're going to do is multiply the conjugate. The conjugate of a binomial is pretty much the exact same thing as the binomial itself, except we change the sign that's in the middle. So we're going to multiply by 1 plus cos x. Now, if I multiply 1 plus cos x over 1 plus cos x, really essentially what we're doing is we're multiplying by 1, because anything over itself is equal to 1. So we haven't changed any value of this equation. What happens when we do that is numerators times numerators. Now what I'm going to do for the numerator is I'm just going to leave it and not distribute. So sine x times 1 plus cos x. But I really want to distribute the bottom, and I'll show you why that's important in a second. So if I were to do the distribution, 1 times 1, 1 times cos x, negative cos x times 1, and then finally negative cos x times positive cos x will give me a negative cos squared x. Now, the reason that we multiply by the conjugate is twofold. First, the terms in the middle, you'll notice, go away because we have plus cos x, take away cos x. So all we're left with is really sine squared x times 1 plus cos x, and then on the bottom 1 minus cos squared x. And so the conjugate was great because the two middle terms go away, but now we're not left with just 1 minus cos x, because if you look at the right side, it would have been really awesome if this was 1 minus cos squared x, because 1 minus cos squared x is part of the Pythagorean identity, which we ended up with eventually. So 1 minus cos squared x is really equal to sine squared x. And now you can see that the sine squared x's will cancel out, and all we're left with is 1 plus cos x. And again, if you'll notice, there's the left side there. We end up with the same answer, left side equaling right side. So you'll notice from this example that there's no one correct way to do an identity. So as long as you're doing all the substitutions correctly and all of your steps correctly, a lot of people's left sides and right sides might look different from each other. Okay, as long as you do get left side equaling right side using appropriate methods, then you're good. So that's it for the lesson today. If you have any questions, please make sure you ask in class. Take care, guys.